Good morning to all of you. Today we will discuss the topic applications of multi-rate signal processing. Till now we have seen different topics like what is the how to implement multi-rate signal processing, and after that we have seen how to get the multi-rate signal processing by multiple stages. We have seen it. Now we will see the applications of multi-rate signal processing, because in almost every application of the image processing, data compression, and in almost all communication applications, this multi-rate signal processing like mobile communication and wireless communication, in all the advanced communication systems, this multi-rate signal processing nowadays we are using. Okay, now we will see what are the different applications of this multi-rate signal processing. Now the first application is subband coding of audio signals, and second one is oversampling analog to digital and digital to analog conversions. These two we will see. There are more applications are there, but we will discuss only 2 or 3 applications. Okay, first we will see what is subband coding of audio signals. Okay, subband coding of audio signals means how to code the audio signals with respect to the frequency band. Okay, because we will see what is the need for this subband coding. If you see the audio signals, so most of the energy concentrated at the low frequencies, as we know that audio frequency band or speech signals are having the frequency band like so 0.3 kilohertz to 3.4 kilohertz. This is the general conversation frequency. So when you consider the frequency components and energy, most of the speech signal energy is concentrated at low frequencies. So and less energy is concentrated at the high frequencies. So that is why, so if you follow the uniform coding or uniform quantization, so you may not have good quality of the speech. That is why, so we have to code it separately at low frequencies and high frequencies. So that is why what we have to do is, so we have to code it separately at low frequencies and high frequencies. So subband coding, the necessity of subband coding is, that is the reason why we have to code it separately. So most of the energy of the speech is concentrated at the low frequencies and less energy is concentrated at the high frequencies. So that is why we need to represent that low frequency signal with a high number of bits and a high frequency signal with a less number of bits. So that is the necessity of subband coding, because so if you code this frequency means the voice signal with the same number of bits, then what happens is they will be uniformly treated. Every energy component or every frequency component is represented with a uniform number of bits. So you may lose some quality of the signal. So to improve the quality of the signal, what we have to do is, so we have to code it separately at low and high frequencies. Okay, so now at low frequencies the energy is more, as we know. So that the frequency, the amplitude component at low frequency is coded with a higher number of bits, and the amplitude at low frequency, high frequencies is coded with a less number of bits. Okay, so therefore we have a different criteria at low frequencies as well as at high frequencies. Okay, that is why we need a subband coding. Coding is different at low frequencies and high frequencies. We will use a high number of higher number of bits at low frequencies to code the amplitude, and we will use a less number of bits to code the amplitude at high frequencies. Okay, that is what we have to consider, and that is a need for this subband coding of audio signals, because audio signals most of the energy is concentrated at low frequencies. Okay, and second one is oversampling A to D and D to A conversion. So when you do the oversampling, then what happens is there is a very large correlation between the adjacent samples, and in that also we'll use this multirate multirate signal processing. Okay, first we will discuss about this subband coding of audio signals. Okay, we will see. So x of n is the original initial signal or sequence, a discrete time sequence. So initially, this subband, this x of n is passed through the low pass filter and high pass filter. Okay, we know the property of the low pass filter, which passes the low frequencies or the frequencies up to a cutoff frequency, and which stops the frequencies above the cutoff frequency. Okay, here this omega is the frequency range from 0 to pi by 2. When omega is, the meaning of this is for the frequencies between 0 to pi by 2, frequencies are allowed here, and the same x of n is given to the high pass filter. So what this high pass filter do? It passes the frequencies from pi by 2 to pi. Okay, now we will see. So this x of n is passed initially through the low pass filter, and after that we will downsample by 2. M means actually it is a interpolating factor, and that m value is 2. Okay, now that signal, whatever the signal after passing through this low pass filter, that is downsampled by 2. Okay, now see, this x of n is passed through the low pass filter, and after that you will have a spectrum like this. This low pass filter passes the spectrum between 0 to pi by 2, and after that, and it is downsampled by 2. Now you see this coming here, bottom branch. So here high pass filter is there. This high pass filter passes the frequencies from pi by 2 to pi in the range of omega, and after that it is downsampled. And after downsampling means we know that suppose m is equal to 2 means, so 2 minus 1 or m minus 1 samples are discarded, which are present at the input of the decimator. Okay, decimator decimates or eliminates m minus 1 samples from its input samples. Suppose in the input if we have a 10 samples, out of the 10 samples m minus 1, here m is 2, so 2 minus 1, that is 1 sample is discarded from the input sequence. After that, and every sample is coded. So this encoder is there. Encoder, the job of the encoder is it will encode the database. Suppose if you have a sample of 2 volts, example you assume that a sample is there which is coming with a 2 volts, and this 2 volt sample is converted into, suppose if we have a binary representation, so 0 1 0. So this is the binary representation for these 2 volts. Okay, like that, for every sample which is coming from the decimator, it will encode accordingly according to the amplitude of this sequence or sample. Okay, and that coded speech is stored somewhere for the further future purpose. Okay, that is what is happening in this branch, and it is not further assigned. It is not further processed, because we need to process only low pass signals. Already we have seen subband coding of audio signals. We are not interested in the high frequencies, because only frequency of the speech signal. Okay, this is the speech frequency, speech signal frequency. Okay, so this is the speech signal frequency range, 0.3 kHz to 3.4 kHz. Now, because it is a low frequency signal, only we will concentrate on the low frequency spectrum. So that is when now see this m is 2. After that we will have and after completion of these two, now originally the spectrum is from 0 to pi. Originally the spectrum is 0 to pi. Now what is happening is, you can clearly observe here. So the spectrum is divided into 0 to pi by 2. That is what is happening here, 0 to pi by 2. And after that, in the bottom branch, from pi by 2 to pi. So pi by 2 to pi. That is what we have to understand from this discussion. So therefore, low pass filter passes only from 0 to pi by 2. So this is a 0 to pi by 2. Low pass filter passes, and high pass filter passes from pi by 2 to pi. So overall, so you have a pass band of from 0 to pi. Okay, this is the first stage of subband coding. Means we are separately coding high frequency sequence and low frequency sequence or low frequency signal. You see, now we are stopping. We are not further subband coding this encoded sequence. Simply we are taking that and we keep it stored somewhere for the future use. Now after that, now whatever the signal or whatever the frequency coming from this 0 to pi by 2, I hope you can understand. This is applied to here, and the second is available here. Second one is available from pi by 2 to pi, so that will come here, and from 0 to pi by 2 it will come here. Okay, now what happens? So after this, the from 0 to pi by 2, that spectrum comes here, and the remainder after downsampled by 2, that sequence is given to the low pass filter here, and again downsampled by 2, again downsampled by 2. So therefore, what happens now? It will pass only the frequencies from 0 to pi by 4, and this high pass filter is there from pi by 4 to pi by 2. So therefore, what is happening here? Now here only from this 0 to pi by 2 spectrum is splitted again or coded again, like 0 to pi by 4 in the upper branch, low pass filter branch, and pi by 2 to pi by 4 to pi by 2 in the high pass filter branch. And again, and this high pass filter, after passing the high pass filter, it is decimated, and again it is encoded, and this is a coded speech. Already here we have a coded speech from pi by 2 to pi. Now we have a coded speech from pi by 2 to pi by 4 to pi by 2, and further this low frequency is further passed to another set of low pass filter, decimator and encoder. And finally, so this low pass filter branch passes the frequencies from 0 to pi by 8. So therefore, again this pi by 4, from 0 to pi by 4, this is the total spectrum available. So therefore, from 0 to pi by 4, again splitted 0 to pi by 8 and pi by 8 to pi by 4. You can observe clearly here. So therefore, this low frequency spectrum again broken down into two pieces. First piece is from 0 to pi by 8, that is passed through the low pass filter, and second from pi by 4 to pi by 2, pi by 8 to pi by 4, it is passed through the high pass filter, and again downsampled it further and encoded, output of the encoded is coded speech. You will have a coded speech here. Coded speech. So therefore, again now see, from if you want to further subcode the sequence or subcode the spectrum, then this pi by 8, so pi by half of the pi by 8 is pi by 16. So therefore again you can connect this output to the another low pass and high pass filter branch and decimate it by 2 encoder. So therefore in that case the frequency range becomes 0 less than or equal to omega less than or equal to pi by 16. Okay, from pi by 16 to pi by 8 we have a high pass filter branch. This is how. So therefore pi by 8, half of this pi by 16, and so on, it goes on. So therefore clearly what we are seeing in this discussion is low frequency spectrum is coded heavily, which means with a higher number of bits, and high frequency spectrum or high frequency content, so that is coded with a less number of bits. Okay, so that is what is called subband coding. So subband coding definition, suppose if you want to write the definition of subband coding is nothing but coding the speech sequence or speech signal with a higher number of bits at a low frequency, lower number of bits at high frequencies, and these two are not overlapping. That process is called subband coding. Subband coding means coding differently at different frequency bands. Okay, because we are considering only audio signals or speech signals, so a speech signal mostly concentrated at low frequencies, and the range is 0.3 kHz to 3.4 kHz. So therefore, if you want to code it efficiently, low frequency sequence is coded with higher number of bits, and high frequency signal is coded with less number of bits, so that you can improve the quality of the sequence or quality of the signal, speech signal. and in this way, so we can perform the subband coding of audio signals. And coming to the applications of this subband coding of audio signals is, we have a coding and compression of speech signals. As we have discussed till now, coding and compression of speech signals. So we are coding and we are compressing it. And after, second one is data compression of image signals. Even you can use it for image signals to compress the image or size of the, to reduce the size of the image. Okay, like this, this is the one of the important application of multi-rate signal processing, that is subband coding of audio signals. Okay, now this is a filter used for subband coding. Now we have seen what is the subband coding of speech signals or audio signals. Now the what type of filters used in subband coding. Now this is the filter characteristics or frequency response of the filter characteristics which is used in subband coding of audio signals. Now see this, from 0 to pi by 2. So generally if you see this is a low pass filter characteristics which passes all the frequencies at a lower side, that is you see HLP of omega, which means it is a low pass filter response. This filter, this is a low pass filter response, and after that we have a high pass filter response. These two are combined here. So therefore from here to it is slowly slowly rising, and we have a constant magnitude. Then it is up to pi, it passes all the frequencies. If you combine this, what happens is you get a constant value here, a constant value, which means up to pi it passes the frequencies. That is a quadrature mirror filter. This is called a quadrature mirror filter. And why it is called quadrature mirror filter means we are using low pass filter as well as high pass filter as a combination. That is why it is called a quadrature mirror filter. Such type of filters are used in subband coding of audio signals, okay, or speech signals. So this normally we cannot use only low pass filter or high pass filter. So it is a combination of both the low pass filter and high pass filter. And if you understand this, so it will have a, you see the slope is slowly rising here, it is falling. Wherever exactly, if you want to draw it, so exactly it looks like this. The slope looks like this. And then what happens here, it is maximum, it is minimum. Slowly what happens is, suppose if you have 1 here, it is 0, and 0.9, 0.1. So therefore you will get a constant characteristics from 0 to pi by 2. Such type of filters are used in subband coding of audio signals. Now we will see the second application of this multirate signal processing, that is used in oversampling analog to digital conversion and also digital to analog conversion. In these two we will use a multirate signal processing. Now first we will see oversampling analog to digital conversion. Analog to digital conversion. First see, if you want to convert, generally what is A to D converter? A to D converter is a circuit, or otherwise it is a device or circuit, normally circuit which converts analog signal to digital signal. Okay, now analog signal is X of t. This X of t is applied to sigma delta modulator, so which is generally in this sigma delta modulator. So we have a sampler, and after that, so we have after sampling we have a quantization. All these operations are performed in the sigma delta modulator, and after that we will have a, so 1 bit per sample. We have the samples which are every sample is represented by 1 bit. Okay, so after that we will have a digital filter and decimator, and what it will do is it will downsample the sequence according to your requirement. Suppose see m is equal to 2 means downsample the signal by 2, which means one sample is eliminated from the sequence of samples. Suppose if you have as you have seen 5 samples are the inputs, input are 5 samples, then so m is 2, one sample is eliminated. And after what is here we have a very high sampling rate. Okay, after that we will down convert it to the low sampling rate using this decimator. The purpose of decimator is, so we downsample the sequence, so then the sampling rate is less. After sampling, and we have a very high precision signal, which means the sample value is a very, means the whatever the output you are getting, that is very closely related to the input. And after that we will have a low pass filter, so which is a digital noise shaping filter. Generally it is a low pass filter which passes all the frequencies. Okay, so therefore here we get the digital output, that is X of n. Okay, every sample is noise is removed using this digital noise shaping filter. Okay, so this is the oversampling A to D conversion. What is happening in oversampling A to D conversion? X of t is applied to the delta sigma modulator, sigma delta modulator, and we get the high sampling rate here because it is a combination of sampler and quantizer, and we will have the samples. We will have the samples, and that is a very high number of samples are present, high sampling rates. Sampling rate means what? Number of samples taken per second. Okay, number of, suppose 10 samples per second, 100 samples per second, like that. Number of samples taken per second is called high, generally we say that sampling rate. And that number of samples, and every sample is represented by single bit. And after that we will have a digital filter and decimator which downsamples the already available sequence or quantized sequence. Then after that we will have a digital noise shaping filter, so which passes which removes the unwanted components or unwanted frequencies present in the sample signal. Okay, this is how oversampling A to D conversion takes place. Here we use a decimator. You see this decimator. This decimator, actually, what is the meaning of this decimator? This decimator is one of the multirate signal processing tool. Okay, we have seen decimator and interpolator. These are the two basic building blocks of the multirate signal processing. So because we are using decimator here, so it is actually this oversampling A to D conversion is an application of multirate signal processing. Again, coming to the next one, that is oversampling D to A conversion. So oversampling, now what we are doing, so we are converting digital signal into analog signal. Okay, now the digital signal, we take the digital signal X of n, and X of n is converted to xt. You see here, you observe here, this is analog signal xt, so digital signal xn. Now we take that input, digital input, now we convert into a continuous time sequence, signal xt, not sequence, exactly it is a signal. Now what we do is, first we will have X of n, that X of n is passed through a filter, a digital high pass filter, and after so what it passes the frequencies above the cutoff frequency. High pass filter means which passes the frequencies above the cutoff frequency, and then what happens is we will have a low sampling rate, and so here you will have a images, multi images will be there, and that images are eliminated by this anti-imaging filter and interpolator. Okay, interpolator, what it will do? Interpolator adds L-1 zeros, L-1 zeros between two adjacent samples. Okay, actually that interpolating factor is represented by L, decimating factor is represented by M, you know that. So therefore this interpolating factor L, and whatever the sequence that is coming, so that is upsampled by L. So therefore what it will do is, so X of n is passed through the high pass filter, and after that so you have a low sampling rate, and then so we have a interpolator. The job of interpolator is it will add additional samples between the two adjacent samples, or L-1 samples between any two adjacent samples. Suppose if L is 2, so L-1, 2 minus 1 samples are introduced between two adjacent samples, and so therefore then what happens, see, suppose I have initially I have two samples here like this, one sample here, another sample. So in between, now we have two samples. When one sample additionally added here or inserted, then sampling rate increases. That's why you get high sampling rate. So the interpolator operation in this is, so it will increase the sampling rate. After increasing the sampling rate, we will have a sigma delta modulator, and so this sigma delta modulator again further it will process the signal, and after that this means it is exactly opposite processor. So now we will have a 1 bit sample. Okay, for every sample already 1 bit per sample you will have here, means every bit is represented by one sample, and after that, so every means continuously bits are transmitted or passed through the 1 bit digital to analog converter. Suppose see, so you have I have an amplitude of 2 volts or 1 volt. I have an amplitude of 1 volt. So for this 1 volt is represented by 1 bit only. So therefore that one sample, so I have a bit 1 like this. I have a bit 1. That bit 1 is converted into corresponding equivalent 1 volt sample like this. A 1 volt bit, otherwise a binary bit 1 is converted into a sample of amplitude 1 volt by using this 1 bit digital to analog converter, and after that we will have a continuously, so 1, 2 volt and 3 volts like that, 0.5 volts, maybe whatever may be the sample amplitude, and those samples you will get here. So these things are happened here, and after that, and all these samples are passed through the low pass filter. What low pass filter will do? Low pass filter removes the high frequency component present in the sequence. Then what happens? You will get a, see, it will hold the value here, then smoothly it goes, and finally you will get a continuous message signal here, x of t. X of t is a continuous message signal. How you will get that x of t? So by passing samples through the low pass filter. Low pass, whenever if you pass the samples through the low pass filter, what it will do is it will get a generally staircase signal, and if that staircase signal further smoothened, you will get a smooth message signal, that is a continuous time signal. So therefore, where we use this oversampling A to D conversion, oversampling D to A conversion in mobile phones, we see that whatever we speak that goes to air, and whatever the signal is coming from other side, we will receive it. In both the cases, whatever we speak, that is a continuous signal, and if you want to transmit that, we have to convert it into the digital. In that case, we will use a oversampling A to D conversion. After getting signal is received at the receiver, first of all that signal down converted, and after processing that, we have to get the continuous signal, because this is actually the transmitted signal x of t here, x of t. So therefore finally also you must get the signal that is in the continuous form. So whenever the signal is in continuous form, continuous signal, then only we can get the real voice or quality voice. That is why, so we will again convert from digital to analog signal. So therefore, like this, we will use oversampling A to D conversion and oversampling D to A conversion. In these two applications, decimator and interpolators are there. As they are, decimator and interpolators are present in this oversampling A to D and D to A conversion. So we say that it is an application of multirate signal processing. Okay, thank you. I will stop here. Okay.